Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler, and today we'll be doing Unit 10, Lesson number 8 on the volume of prisms and cylinders. Alright, so volume, is the primary consideration when you go into 3 dimensions. Alright, so let's start by talking just a bit about volume. Volume is the measurement of the amount of 3-dimensional space that lies within a geometric solid. All right, and we measure volume in many different ways, right? When I say something like, I'm going to go pick up a gallon of milk, gallon is a measurement of volume. A liter is a measurement of volume. But very often when we're in a geometry class or a measurement class, we measure volume very similar to the way that we measure area, in that we're trying to count or figure out how many cubes of a particular size fit into an object. So for instance, if you've got this cube, that measures 1 inch by 1 inch by 1 inch, and let's say that's the same cube here, if I'm measuring this volume, and I call this a cubic inch, then the question becomes, as I take these cubes and I put them in here, how many of them are going to fit into this box? And again, I may have to slice them up so that I have a half of a cube or something like that, and I'm not going to fill up the entire box. But ultimately speaking, when I measure the volume in this box and I say, oh, the volume is 12 cubic inches, what I'm saying is that 12 of these things fit inside of that box. And if I say it's 12 and a half of them, it just means, well, I got 12 in, then I had to slice this thing in half and drop it in. All right, so let's start by reviewing how to calculate the volume of a very simple solid. All right, now remember, we're talking about prisms here, And a prism is an object that has a base and another base that are congruent to each other, and all the sides are parallelograms. The simplest of all prisms is a rectangular right prism, and that's what we have here. So let's take a look. Exercise number 1, a rectangular right prism, or box, has a length of 8 inches, a width of 4 inches, and a height of 5 inches. What is the area of the base of the box? Use appropriate units. Well, this should be a piece of cake for you. Take a minute and figure out the area of the base. All right, well, ultimately speaking, the base is this rectangle that is 4 inches by 8 inches. And so its area, 4 times 8, is 32 square inches. And again, all that means is that I can fit 32 unit squares in there. 32 squares that are 1 inch by 1 inch. Simple. Now letter B asks us, what is the volume of the box? Use appropriate units. This is something you've seen before, so I'd like you to take a shot on it on your own, and then we'll talk about it. Don't worry about the rest of the question, we'll get there in a moment, but just figure out what the volume of the box is. All right, well, let's talk about it. I'm sure as early as 5th grade, you saw the formula that said the volume of a box is its length times its width times its height. All right, so in other words, this particular box would have a volume of 8 times 4 times 5. All right, you might need to use a calculator here, maybe you don't. But if I do all the calculations in my head correctly, that's 160 cubic inches. And again, keep in mind, what I'm doing is I'm counting how many of these unit cubes fit inside of this box, A cube that's 1 inch by 1 inch by 1 inch, 160 of them exactly fit into that box. Now, more importantly, it says, how can you use your answer to part A to determine the volume? You might think, I don't need to use my answer from part A to determine the volume, but this is pretty critical for what we're doing both in this lesson and the next lesson. So think about that for a minute. How can you use that 32 square inches to come up with that 160 cubic inches? All right, well, it's not too bad, In fact, let me just switch to a different color for a minute. All right, notice, the calculation of the area, 4 times 8, is sitting in the calculation of the volume, 4 times 8. So you could actually say that the volume, let me scroll down here a little bit, that the volume is simply the area of the base, times the height. And that, I hope, makes a lot of sense to you. I want you to just think about this for a second, right? What that 32 square inches means is that I can take that base and make 32 of those squares fit inside of it. And for every single one of those squares, there are 5 cubes that can sit on top of them. So literally, when we take the area of the base and multiply it by the height, that gives us then the volume. And many times with prisms, what you see is the following formula. All right, the volume of a prism is simply B times H, where B is the area of the base and H is the height of the prism. And it doesn't matter whether it's a rectangular prism or a prism like this where we've got, a pentagon as a base and a base. All we have to do is take the area of the base, which is how many squares fit inside the base, and multiply by the height, which is how many cubes can be stacked on top of each one of those squares, and we get the volume. Now, one thing that I've always found a little bit confusing when the volume formula is written like this, let me write it a little bit higher, is it almost looks like that's an area formula. Oh, I got, something times something. Except this, all by itself, is an area, right? It's the area of the base, right? So it makes sense that I'm taking an area, multiplying it by a height, and then getting a volume, all right? Let's take a look at one that is much, much more challenging than the last one. Exercise number 2. A prism has a base that is an equilateral triangle, very important, equilateral triangle, whose sides measure 6 inches each. The height of the prism is 8 inches. What is the volume of the prism to the nearest cubic inch? So the approach here is relatively simple. The volume is going to be the area of the base times the height. Now the height we have, it's 8 inches. But the area of the base, that is much, much more complicated in this scenario. And think about why that is, right? The base is an equilateral triangle, right, that measures 6 inches on each side. Now, it would be tempting to just say, well, I'll figure out the area of that triangle by doing 6 times 6 and then multiply by 1/2 base times height. The problem is, of course, that 6, if this 6 is the base, that 6 is not the height. So one thing that makes this problem rather challenging is that you have to figure out what the height of this equilateral triangle is, not the height of the overall prism. We know what that is. That's equal to 8. But you've got to figure out the area of this equilateral triangle. Why don't you spend a few minutes and try to figure out the area of that equilateral triangle? Don't worry about working at it as a decimal. Just figure out its area if you can. All right, let's go through it. Well, in order to figure out the area of that, we've got to figure out its height, right? And in order to figure out its height, we've got to cut that equilateral triangle in half. That's 6, that's 3, we need our height, and I've got to do the Pythagorean theorem to figure out that height. It's not that bad. Just do it right over here. I'll do h squared, maybe I won't use h, because I've already used h here. I don't want you to be confused about that h and that h, because they're not the same. Maybe I'll call it just a in the Pythagorean theorem. We'll do it right here. A squared plus 3 squared is equal to, already squaring the 6, 6 squared. A squared plus 9 is equal to 36. Subtract a 9 from both sides. Maybe give myself a little bit more room. A squared is equal to 27, and a is the square root of 27. Now keep in mind what that really is, right, is it's the height of that equilateral triangle. So now we can actually calculate the area of the base, okay? So let me do that, right? The area of the base is going to be 1/2 times 6 times the square root of 27. Now you could actually leave it that way if you wanted to, or you could simplify it, or you could come up with a decimal version of it, keeping in mind though that if you come up with the decimal version, you don't want to round it. Notice here it says round to the nearest cubic inch, never round an intermediate answer. Now one thing I'm tempted to do, I'm tempted to just use the associative property of multiplication and say, well, I'm going to multiply those two, right, and get 3 times the square root of 27. Some of you may even have the urge to simplify the square root of 27. You can do that, but you don't have to. Let's now figure out what the volume is. The volume is now going to be 3 times the square root of 27. Again, that's just the area of the base, times now the height of our prism. That's my 8 inches up here. And now this, I'm going to throw into the calculator just like that. 3 root 27 times 8. Let me jump out of here really quick. Here we go. 3 times the square root of 27 times 8. Make sure that 8 is not underneath the square root. If you have to, you can put parentheses around the 3 root 27, or you can move the 8 out front. Either way, our volume now is 124.7, etc. We needed our volume rounded to the nearest whole number, I think it was, the nearest cubic inch, so that's going to be 125 cubic inches. Just checking over on my answers. Let's go back into here. 125 cubic inches. Now the hardest part of this problem, keep in mind, wasn't doing the volume calculation. It was actually coming up with the area of the base. And that was challenging because we didn't know what the height of that triangle was. All right? Watch out. Make sure you know what you know what you don't know, and especially you know what you need. So if I have to calculate the volume of a prism, I need the area of its base and its height. Identify what you don't have about that, and then just use the tools that you've learned in geometry to calculate it. Let me step out of the way so that you can copy any of this down, then we'll do some more work with the volume of prisms. All right. Now, what is the key to a prism? The key to a prism from the last lesson is that the top base and the bottom base are congruent to each other, and any cross-section that I make horizontally is congruent to those bases. Something that has exactly the same property as that is a cylinder, right? Where we've got the top being a circle, the bottom being a circle, and anywhere I slice it horizontally, I'm going to have the same circle. When you have that kind of scenario, what it means is you'll still be able to calculate the volume by simply taking the area of the base and multiplying it by the height. So let's take a look at this problem. It's a very quick problem, but let's take a look at it. Exercise number 3. A cylinder is a solid that follows the same rules as a prism because it has a constant cross-sectional shape and area. Explain why the volume of a right circular cylinder is given by this formula. Now, this is kind of a classic formula. You'll see this in any book pretty much on high school mathematics and above, the volume formula for a cylinder. Often on things like the SAT math section, this is a formula that they will not give you. They'll just expect you to be able to know it. So why does this formula make sense? Think about that for a moment. Write down whatever you can. All right. Well, here's why. For any shape with a constant cross-sectional area, the volume is equal to B times H. Right? For anything where the cross-sectional area keeps staying the same, the volume is the area of the base times the height. But for us, the base is a circle. Hello. A circle. So B is equal to pi r squared. Right? That's simply the area of a circle. And therefore, the volume of a cylinder is going to be pi r squared. That's equal to the base area times the height. All right? I don't know that I would even memorize this formula, quite frankly, because as long as you know for a constant cross-sectional area, you take a constant cross-sectional area, you calculate the volume by doing the base area times the height, then as long as you know the area formula for a circle, the volume formula for a cylinder should be easy. Let's actually go ahead and do a problem on that. Well, actually, I guess not yet. Let's talk about Cavalieri's principle, all right? So far what we've been looking at is we've been looking at prisms where the height is perpendicular to the base, all right? Like literally the sides that move up. We've been looking at right prisms and right cylinders, okay? Cavalieri's principle says we don't need to worry about that. Now, before we kind of get into this, all right, keep in mind, right, with triangles, right? When I have a triangle, a right triangle, and I have a base and I have a height, we all know that the area is 1/2 base times height. But we can also kind of skew that triangle like this. And yet we still know that if that's the base, and we know this distance as the height, then we can do 1/2 base times height. Well, Cavalieri's principle essentially says the same thing works for solids and volumes. Two solids that have equal cross-sectional areas at all heights have equal volumes. Wait, what? Two solids that have equal cross-sectional areas at all heights have equal volumes. The classic illustration of this, believe it or not, has coins involved in it. And here's what I mean. Right, I've got these two stacks of coins, gold dollars, if you will. And they have exactly the same number of coins in them, all right? Exactly the same number. And therefore, the volumes of these two things, and they would both be cylinders, by the way, the volume of these two cylinders has to be the same. It's got to be the same, even though that one's slanted, right? And we could calculate the volume in both cases by simply knowing what the area of the circle is on the top and then multiplying by the height, regardless of whether we measure the height this way or whether we measure sort of the height this way. It doesn't really matter, right? These two things have to have the same volume because they have the same cross-sectional areas, even though this one's kind of tilted over. And again, the key is when we do that volume equals base times height, we still want to figure out the base area, right? And then we just multiply it by the height of the overall solid. Okay, and it's kind of a cool principle, right? It just basically says that it doesn't have to be a right prism anymore. It can be kind of slanted over. So let's play around with that. All right, here we go. A non-rectangular prism, or a non-right prism, has square bases, very important, square bases, two vertical faces that are rectangles, and two vertical faces that are non-rectangular parallelograms. Whew! The side view of the non-rectangular parallelograms is shown. That's what we've got right here. All right, determine the volume of the prism to the nearest cubic inch. All right, well again, the great thing about the volume formula for a prism, right, base area times height, is that essentially we just have to know two things. We need to know what the base area is, and we need to know what the height is. All right, now, keep in mind they've told us, even though the picture may not look this way, that the base of this prism is a square. So actually calculating the base area should be pretty simple as long as we know what the dimension is of the square. Well, there it is. It's 4 inches, right? It's going to be 4 inches by 4 inches. So B is really relatively easy. It's 4 times 4, or 16 square inches. Now the harder part is the height, and the height is most certainly not 7 inches, right? The height is going to be this distance, right? There's our height. So the question is, how can we find that height? Okay, think about that for a moment. See if you can figure it out. All right, well, when you've got an angle and you've got a length, think about right triangle trig. In fact, let me kind of clean this up a little bit and draw it right down there. What we've got in this scenario is we've got this side length of 7. We've got this angle of 58 degrees. It's kind of the tilt of our prism. We need to know what the height is. All right. So we're going to use right triangle trig, and specifically, because the height is the opposite side and the 7 is the hypotenuse, we're going to use the sine ratio. All right? We can say that the sine of 58 degrees is equal to h divided by 7, multiply both sides by 7, and the height now of our prism is 7 times the sine of 58 degrees. Completely okay at this point to work that out in terms of a decimal, as long as you don't round early, right? Only round your final answer. I'm going to leave it this way because look at what I can now do. I can now say that the volume is 16, that's my base, right, times 7 sine 58 degrees. And I'm just going to put that into my calculator just that way. 16 times 7 sine 58. Let me clear that out. 16, remember, that's my base area, times 7 sine 58. All right, that's my height. All right, wait a second. Oh, good. I'm in degree mode. I always want to make sure. Right? And I end up getting 94.98. I think to the nearest cubic inch, that would be 95. I think that's what we wanted. Let's see, nearest cubic inch. Yep, 95 cubic inches. All right, so we had to do a little bit of trigonometry. In that first problem where we had the equilateral triangle, we had to do a little bit of Pythagorean theorem. In this case, because we've got an angle and a slant length, we had to use trigonometry to figure out what the height of the prism was. But ultimately, what Cavalieri's principle allows us to do is it allows us to simply say the volume is going to be the base area times the height, right? Even if that height is not one of the sort of side lengths of the figure, okay? Let me step out of the way. You go ahead and take a look at this for a minute, and then we'll move on to our last problem. All right, let's do it. Okay, chicken coop. I mean, how many times have we done chicken coop problems in this course? Many, many times, I know. Let's take a look at it. Exercise number 5. A chicken coop is in the shape of a prism shown below. Determine the volume in cubic feet of the coop. Show the calculation that leads to your answer. A prism? Is this a prism? Sure it is. Remember, what a prism is it's a three-dimensional object where two of the faces are congruent and all the other faces are parallelograms. So in this case, the prism just isn't oriented so that it's sitting on one of those two congruent bases. But this front side, right, this pentagon here, and then the pentagon on the back side are identical to each other. And then these faces, right, these 5 faces, are the ones that are all the parallelograms. All right, so it's definitely a prism. And again, the volume of a prism is going to be the area, right, the area of the base times the height. But remember, that base now is the area of those two congruent faces. I mean, not put together. So think about this a little bit and see if you can figure out the volume of this chicken coop. All right, let's take a look. Well, in order to do that, I need to figure out the area of this thing. This is my B, right? That's my base, okay? My base is not this rectangle. It's not the thing the prism is sitting on. It's the two congruent faces. So I got to figure out that area. All right, and that actually is going to take a little bit of work, right? Because this thing is a combination of a rectangle along with a triangle. But that's simple enough. Let's see. What do we have? Well, for the rectangle's area, we have 10 feet times 7 feet. And of course, that's going to give me 70, but whatever, right? And then I've got another portion up here, right? And that's a triangle. Of course, the area of that triangle is going to be 1/2 of its base, all right, which is 10, times its height, which is another 4 feet. All right, and then that actually ends up being 20. So the base area is 90 square feet. All right, now that's just the base area. Now what I have to do is I have to multiply it by the other dimension, okay? The quote height here. And again, that's actually this. It's that 12 feet. Imagine taking this chicken coop and kind of turning it so that it's literally sitting on one of those two pentagons. So now my volume is going to be 90 times 12. And of course, that's easy enough. Let's just really quickly come over here, clear. 90 times 12. And we get a volume of 1,080 cubic feet. (1,080 cubic feet. All right, take a look. All right, and then let's take a look at letter B. If the entire volume of air must be moved out of the coop in an hour, how many cubic feet per minute must the fan move in order to accomplish this task? All right, so very often in chicken coops and other sort of livestock containment systems, yes, I went there, right? Air has to be moved in and out on kind of like a minute-by-minute basis to keep the air fresh. So the question is, if I have to move all of this air, all 1,080 cubic feet of air, in 1 hour, how many cubic feet per minute do the fans have to move? All right, think about that for a minute. It's not too tough. All right, well, we're just talking about a rate, right? This is how much we have to move, and we have to move it over the span of 60 minutes. So at the end of the day, all I need to do is figure out what 1,080 cubic feet divided by 60 minutes is. Right, and again, simple enough. Let's go back to here. I've got that right there. I'm just going to do divided by 60. And so the fans must move 18 cubic feet every minute. 18 cubic feet every minute. That sounds like a lot, but it's not too bad. So that's 18 cubic feet per minute. All right, and that's it. Okay? Not too bad. Let's wrap up. So in today's lesson, we started to look at volume, the amount of three-dimensional space that fits inside of any object. And we really just looked at it for three-dimensional objects with constant cross-sectional areas. Those are the prism and the cylinder. And in those cases, it's very simple. We need to figure out the area of those constant cross-sectional areas, okay, the area of the base, and then we need to multiply it by the height, or the other dimension, the dimension that sort of connects the two congruent bases. All right, and I kind of want to say it that way as opposed to the height, because in that last problem with the chicken coop, we'd kind of think about the height of the coop as being from the ground up to the top of it, but that's not the case. It was really sort of the length of the coop, if you will, because the two congruent faces were the front and back of the coop. All right. We also learned about Cavalieri's principle, which says that even if the prism is sort of tilted, ultimately speaking, we still just take the area of the base and we multiply it by the height. And you've seen that before in terms of areas with parallelograms and triangles, and now we just extend that to three-dimensional objects and volume. All right, next time we're going to be looking at the volume of pyramids and cones. That's going to be fun. But for now, I'd like to just thank you for joining me for another Common Core geometry video by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.